Hello and welcome. In this video, we're going to be looking at the review packet for AP Physics 1 rotational motion. This will include rotational kinematics, rotational dynamics, including balance torques and net torques, as well as rotational energy, rotational inertia, and angular momentum. This will include review packets 8 and 9 together. Remember to pause and rewind the video as necessary. Let's begin. Problem number 1. The objects labeled M all have the same mass. All 4 situations have been shown to be in equilibrium. Rank the masses A, B, C, and D from greatest to least and explain your reasoning. So we know that mass M is the same, but A, B, C, and D could all be different. Some of them might be the same as well. Let's take a look and examine each one of these cases. One thing to note that this is a balanced torque problem. Which means we need to know our basic torque equation. Torque is equal to a perpendicular force times distance. However, when all of your forces are essentially weights, mg and mg, well, g's are going to cancel out of the equation when you start setting forces and torques equal to each other. Thus, the equation can really be simplified from force times distance to mass times distance. Something to consider. Well, if we look at case number 1, I'm going to number these cases so that we can have something to rank. So case number 1 has block A, case number 2 has block B, case number 3 has block C, and case number 4 has block D. Well, A equals M. If you look, A and M have the same distance, and they're 2 units away from the fulcrum. D is also equal to M, 1 unit away from the fulcrum. So if D equals M and A equals M, then perhaps maybe A equals D. We also know C is twice the distance, so C is going to be half the mass because it's twice as far from M. So you can see M is 1 unit away, C is 2 units away. So twice the distance, and this is where we can reason out using this equation here. If the torques are balanced, then twice the distance means half the mass. These two have to balance each other. So C is going to be half of M, so C will be less than A and D. And then B is going to be 2M because B is half the distance. So it's 1 unit of distance versus 2 units of distance. So half the distance, that means block B would be twice the mass. Thus, block B is the largest, followed by block A and D being equal mass, followed by block C. Problem number 2. A regular hexagon pivoted at the center has 4 equal forces A, B, C, and D applied to them. Rank the forces on the amount of torque they produced from greatest to least. So remember, what this means is they're same force, but what we want to know is we're ranking the torques. What is the greatest torque produced by these forces versus what is the lowest amount of torque produced by these forces? Well, we can immediately go to the lowest amount of torque, and that's this. Here is the center, right here. And if you notice, force C and force B are both, if you examine this as the distance from the pivot to where the force is applied, that is a parallel force. Torque is a perpendicular force times distance. Parallel forces do not do any torque. So the least amount of torque in this problem are B and C. Both B and C essentially produce zero torque, so they're the least. Now, if we look at A and B, A is actually going to be the most. And that's, if you notice, it's producing a force that's perpendicular to this lever right here. That means that's the greatest amount of torque because it's already a perpendicular force. Whereas D, well, here's the lever, and you can see the force is coming in at an angle to the lever. So if we were to do this and create vector components, that's my angle right there, then it's really, if this is my force, it would be force cosine of theta. That is actually what is going to be applying the torque. And force cosine of theta would mean that this is going to be a smaller torque than this one right here because it has less of a force applied to it. F cosine theta is less than F. So again, just to summarize, B and C push at the fulcrum, so no torque. A is perpendicular to the radius, so that is complete torque. And D is at an angle to the radius, which means it's some perpendicular of d sine theta, or you could say d sine theta or f cosine theta. What depends on what you're looking at. Either way, it's going to be less than the actual force applied. Part B, the torques produced by the force result in a net torque. Is the net torque on the hexagon clockwise or counterclockwise? Explain your reasoning. Well, these forces do not contribute a torque. No torque, no torque. That's the greatest torque. This is the lowest torque. This would cause the hexagon to spin in the counterclockwise direction. Clockwise direction. This would cause the hexagon to spin in the counterclockwise direction. So clearly, clockwise torque is greater than counterclockwise torque. So the net torque spins in the clockwise direction. Again, there is more clockwise torque than counterclockwise torque because force A is greater than force D. The four forces also produce a net force. Is the net force on the hexagon due to the forces upward, downward, to the left, right, or zero? Well, it's going to be zero. Because if you look at the forces, just look at the direction of forces. Let me erase everything that's on here. Just look at all the forces for a second. We're not talking about torques, mind you, about forces. So equal forces. Down, left, up, and right. Since they're all equal and pointing in completely opposite directions, they all add up to no net force. Problem 3. A pulley consists of two attached wheels. The outer wheel has twice the radius of the inner wheel. In each case below, one or more masses is attached to the wheel and released when the initial velocity shown, if any. On the grids below in each case, sketch a graph of angular velocity omega and angular acceleration alpha of the wheel as a function of time. Let clockwise be positive and counterclockwise be negative. Pay attention to initial values, slopes, and shapes for each graph. Well, one thing we should consider before we begin, when objects speed up, the velocity and the acceleration point the same way. When objects slow down, velocity and acceleration point in opposite directions. And this is true for omega and alpha as well. And we're going to use the same principle. Instead of going left and right or the same direction for acceleration and velocity, we're going to be talking about clockwise versus counterclockwise. Let's take a look. In A, clearly you're starting from rest, and the mass is put on the right-hand side, which means what's going to happen is this is going to accelerate downwards, which means in situation A, we are going to speed up in the clockwise direction. So speed up clockwise, so speed up positive, clockwise positive. This corresponds to positive alpha, positive constant acceleration. So again, our omega is clockwise, and since we're speeding up, our alpha, so this is our omega, our alpha is also in that direction too, also clockwise. Okay. Now, what is that going to look like as far as a graph is concerned? Well, if I'm starting from rest, means I'm starting with constant acceleration, so I should see a constant slope showing the constant acceleration for omega versus time. It's positive acceleration, so constant positive is graphed as a horizontal line above the t-axis for the same length of time. In situation B, well, it's the same as A, but we're given a push to this. We're given an initial velocity going down. So your situation is going to be very similar. You're going to be speeding up in the clockwise direction. So speeding up positive, clockwise positive, that corresponds to positive alpha again, but this time you're starting with an initial velocity. So how do we plot that? Start with the initial velocity, like this, and you will have the exact same slope as you did before. Because it's the same mass undergoing the same acceleration, but from the point of view of that. So your acceleration, since it's the same slope, your acceleration should be exactly the same. Well, in situation C, we're given a push on this mass. It's going to go up, but clearly what it's going to do is it's going to go up, but it's going to slow down. It's going to slow down. It's going to slow down in which direction? It's going to slow down in the clockwise direction. So clockwise positive, but slow negative. So what that means is that's negative alpha. So anytime we have a negative acceleration, we slow down, the acceleration goes opposite the omega. So again, in this case, omega was going clockwise, alpha was going clockwise, but here we're slowing down in the clockwise direction, which means the acceleration is really counterclockwise, okay, or negative. So how do we show that? Well, let's go and let's make a dot at some initial velocity, and we're going to bring that down to 0. We're going to slow down at a constant rate, which would be negative constant acceleration below the axis. Same idea as C. D is the same idea as C, but now you're given a push on the mass on the right-hand side of this, which clearly means what are we going to be doing? We're going to be rotating in the clockwise direction, but you're going to be slowing in the counterclockwise direction, not clockwise. We're spinning that way. So we're slowing in the counterclockwise direction. So slow negative, counterclockwise also negative. Well, two negatives, that corresponds to a positive alpha. So alpha is going to be going in the clockwise direction because, again, it corresponds to positive acceleration. Those two negatives correspond to a positive. So omega, we're starting with an omega, but it's in the negative direction. So start with an omega down here somewhere, and it's slowing down to 0. So go ahead and take it to 0 velocity there, and you can see it's a positive upward slope, which corresponds to a positive upward, positive constant acceleration. Letter E. Now for letter E, you have two equal masses spaced equally apart, which means you actually have a situation here where we will end up with balanced forces. And balanced, not just balanced forces and torques. Okay, so what that means is this is going to move, but it's going to move at constant velocity. So in other words, acceleration equals 0, and since acceleration equals 0, alpha equals 0. There is no alpha in this problem. Okay, now since we're pushing it upward like this, it's going to be rotating in the clockwise direction, or counterclockwise direction, which is negative. So we're going to have constant negative velocity in the counterclockwise direction, but you're going to have 0 alpha, 0 acceleration. So just make a horizontal line right on 0. Okay, now with the situation with F, you are going, let me see here. So what's going on in F? Okay, so we have a heavier mass on the left side, a lighter mass on the right side. And what we're gonna do is we're gonna pull on the lighter mass, but clearly it wants to accelerate in this direction, not in the way that you've pulled it. So what's gonna happen is it is going to slow. But if we're giving it a tug in this direction here, you're moving it initially in the clockwise direction. So it's slowing in the clockwise direction. So clockwise positive but slow negative, so this means negative acceleration. Okay, however, here's the difference. It's going to be much less, since you have so much opposition to that on the other side. It's not really going to be the same as what we did earlier in, let's say, a problem like this, where we have it go upwards and then it goes up and then falls back down again. You have a lot of opposition on this side right here, which means you should expect a lower value of your omega. It'll still drop to 0. So your graph will look the same, but it's dropping from a smaller height. And therefore it has a smaller slope, a smaller, if you're slowing down, your acceleration always goes opposite the spin. So alpha goes in the negative direction. And it's a negative constant alpha. It's very close to 0, but it's not 0. It's just a small value of acceleration. Okay, so what's going on in letter G? So in letter G, you've got 2m on the left side, m on the right side, but if you notice, they're hanging from different wheels. 2m is hanging from a rope off the inner wheel, right here, and m is hanging from a rope off the outer wheel. Well, at time equals 0, when this thing is released, at time equals 0, this is kind of an important idea. At time equals 0, the tension balances the weight, mg. So if I know that I've got a weight of 2 mg this way and a tension pulling up this way, tension is what's causing the torque this way. So essentially, tension equals 2 mg at time equals 0, because we haven't begun to accelerate yet. If we even do accelerate, who knows if we even accelerate. But at time equals 0, there is no acceleration at that moment yet. Okay, so then same idea. This just would be mg. So the torque that results on this one, remember torque, the counterclockwise torque, right, is going to be force times distance. The force would be tension. The distance would be radius. So tension times radius. The counterclockwise torque would be tension, which is 2 mg. Remember, they're equal. In this situation, at time equals 0, they're equal. Times r, the radius. So 2 mgr would be the counterclockwise torque. The clockwise torque, it's also tension times radius, but this time the clockwise torque is equal to the tension, which is mg, times the radius, but the radius is 2r. And if you look, we get the same thing, 2 mgr, which basically means even though we give this thing a, we essentially start it from rest, which means you don't give it a tug in any way, shape, or form since the torques are balanced. There's no rotation. Okay, which basically means you're going to have all the way across here and all the way across here. No omega, no alpha. Okay, and part H, last one, we have equal masses, but again at different radii. So this is at R, this is at 2R. You can clearly see this one would be a greater torque because it has a greater distance. So the tension pulling this way, clockwise torque is greater than counterclockwise torque. Again, just simply looking at the longer lever arm, you should be able to see that. Okay, both have similar tensions because they both have, 2m mass on the other end of it, but the clockwise torque is going to be greater. So what that basically means is, since we're giving it an upward push on the clockwise side, what are we going to be doing? It wants to accelerate in this direction, but you're giving it a push against that. So we're going to be slowing down. Give it a spin in the counterclockwise direction. So negative, negative, which means overall positive constant acceleration. So you're starting with some negative omega because you're giving it negative spin. It's going to drop off to 0. It's going to slow down, which accounts for positive constant acceleration. Problem 4. A student balances a baseball bat on the fulcrum as shown in the diagram. 3 students are then asked to consider what would happen if the bat were cut in half through the point where the bat balanced. In other words, the bat was cut right there. Which piece of the bat would be heavier, the teacher asks. The students reason as follows. Student A says the left side of the bat would have more mass because there is more wood matter on the left side of the fulcrum. The bat is longer on that side. Student B, the right side should be more massive because the right side is closer to the fulcrum than the left side is, and the closer object must be heavier. Student C, the 2 sides must have equal mass since there are equal amounts of matter on both sides of the bat's center of mass. In a well-organized paragraph, explain who is right, why they are correct, and explain why the other 2 students' line of reasoning are wrong. You may use equations, diagrams, but these alone do not compromise a complete response. Ladies and gentlemen, this is a balanced torque problem. Okay, and torque itself is equal to a perpendicular force times distance. We established in the previous example, or one of the previous examples, that when your forces causing a torque are essentially weight, then you can simplify it to mgd, weight times d, and then the g's end up canceling out because we have counterclockwise torques equaling clockwise equal countering clockwise. So you might end up with mgd equals mgd. You see the g's end up canceling, so it's really just mass times distance. So if the torque is balanced and mass times distance is constant, mass times distance is constant, that basically means is greater mass, lower distance. Lower mass, greater distance. Well, it's asking which student would be heavier, so which side would be heavier. So the side that's heavier is the side that is closer to the fulcrum. That makes student B correct. Student B is correct because mass is closer to the center of mass is greater. The mass farther from the center of mass is less. Student A is incorrect. The bat is thinner on the left, but length does not determine mass. Student C is incorrect as the masses cannot be equal because the bat is not a symmetrical object. Number 5. A post that can freely rotate has a meter stick attached to the top at the 50 centimeter mark. In 6 cases below, 4 cylindrical metal masses are attached to the meter stick in different arrangements. A. Rank the 6 cases based on the rotational inertia from greatest to least. Briefly explain how you determined your ranking. So recall, ladies and gentlemen, that the rotational inertia for a point mass is mr squared, and when you have several point masses, you simply add your mr squareds. Let's let each mass be one mass unit. Case A. Again, pause the video as necessary to complete your calculations. Well, if we add up your mass times radius squared for this mass plus mass times radius squared for this mass, why is the radius 0? Because the radius is the distance from the point of rotation to where the mass is located. And if the mass is at the point of rotation, it essentially contributes no rotational inertia. So that is 0, that is 0. And then, of course, we're left with one mass unit, one distance unit away. So that's why we're going 1 times 1 squared plus 1 times 1 squared, which gives you 2 kilogram meters squared for case A. Case B, all the masses are stacked at the fulcrum, I equals 0, because all masses do not contribute to any rotational inertia. Case C, we have 2 in the middle that don't count. So I'm going to zero out both of these. And the 2 at the edge do. We have 1 mass unit, 2 distance units away. So it would be 1 times 2 squared plus 1 mass unit times 2 distance units squared. Well, 2 squared is 4, times 1 is 4, plus 2 squared is 4, times 1 is 4. 4 plus 4 gives you 8 kilograms meters squared. Case D. You have 2 stacks at the end, so this would be not 1 but 2 mass units, 1 distance unit away squared, plus 2 mass units times 1 distance unit away squared. 1 squared is 1 times 2 is 2, plus 1 squared is 1 times 2 is 2, for a total of 4 kilogram meters squared. Case E. All 4 masses are towards the edge. So we have 2 mass units, 2 distance units away, and 2 mass units, 2 distance units away. So 2 times 2 squared plus 2 times 2 squared. 2 squared is 4 times 2 is 8, plus 2 squared is 4 times 2 is 8. Gives us a total of 16 kilograms meters squared. Case F. We have them scattered a little bit. So this one here would be 1 mass unit times 1 distance unit squared, plus this one here would be 1 mass unit times 1 distance unit squared, plus this one here, which would be 1 mass unit times 2 distance units squared, plus this one here, which would be 1 mass unit times 2 distance units squared? Well, it would be 1 plus 1 plus 4 plus 4, or 10 kilogram meters squared. Completing those calculations should help you rank them as E being the highest at 16, which is greater than F at 10, which is greater than 8, let case C is 8, which is greater than D, case D, which is 4, which is greater than case A, which is 2, which is greater than case B, which is 0. Again, each mass unit was 1 unit. We use the equation mr squared, the sum of mr squared, and add all the mr squareds in each case for each mass on the meter stick. Part B. A student is asked to measure the rotational inertia of one of these cases above. In the space below, write a procedure that the student could follow to determine the rotational inertia of the entire system. Include post and meter stick. Explain what should be done with what equipment and what measurements should be made with that equipment. Also explain how the data can be used to determine the rotational inertia. In other words, which calculations you can do. The student only needs to perform one trial. Well, what we can do is we can take each of these setups here, and any one of these setups, and we can essentially take that pole. We're going to assume that pole is a hollow pole, and that meter stick that's attached to it, and we can put it on a ring stand. So imagine now that the pole, let's draw the apparatus here. So you've got the pole, you've got the meter stick attached to it, you've got your masses somewhere on there. Who cares? It doesn't matter because you could use this for any of the scenarios. But let's say this whole thing has the ability to rotate like this because the pole is on top of a ring stand. So you've got the ability to rotate. This meter stick will rotate horizontally, basically. Now, how do we get it to rotate? Well, here's what we do. Take some string, put this on a tabletop, fasten a pulley nearby the edge of the tabletop, and take some string and wrap the string several times around the pole. Pass that string over a pulley to a hanging mass, a hanging known mass over the edge of the table. Now the mass is a distance d above the ground where it is. Pause the video to essentially copy down that diagram. When you release this, we will accelerate downward, which means the whole system will begin to spin in the counterclockwise direction, but it'll spin faster and faster, which means you will accelerate. The tension in the rope causes a torque. You're spinning faster. Which means you have angular acceleration. And then lastly, net torque equals I alpha, which means if we have a way to calculate this and calculate this, we can figure out the rotational inertia. Let's see how this can be done. So let's summarize what we drew here. Place the post and meter stick and masses on a table. Wind up the string several times around the post and run the string over a massless, frictionless pulley attached to the edge of the vertical end of a string. Let the hanging mass fall from rest and record the time t it takes to fall distance d. Use the equation d equals 1/2 at squared to find a. A would be 2 times the distance divided by the time squared. So clearly we need to stopwatch to measure the time it takes to fall and that distance it has fallen. But using that, you can find the acceleration of the block, which is the same as the acceleration of the string at the edge of the pole that's twisting the pole. Then we can use this equation here, A equals R alpha, and solve it for alpha. Alpha equals A over R, where R is the radius of this post here. It's this value here, R, half of the diameter. Using the acceleration, determine the tension that creates the net torque. So in other words, you've got mg going down and you've got tension going up. This tension is the same as that tension. So I would use mg minus tension equals ma. You know this, you know this, you know this, and you know this. Well, now you do anyway. You can figure out the tension using that equation right there. Lastly, figure out what the torque is. Remember, torque is force times distance. So the force is going to be your tension. Use that to figure out what your torque is. And we're going to use net torque equals I alpha to solve for I. Now, for review packet number 9, we're going to take a look at more of the energy and momentum side of rotation. Let's take a look. Problem number 1. 4 objects in order: a hollow sphere, a thin hoop with cart with light wheels, and a solid disc. Each have the same mass, 0.4 kilograms, are released from rest at the top of identical inclines, each with a height of 3 meters. The objects move towards the bottom and reach the bottom with different final speeds. The sphere, disc, and hoop all have the same radius and do not slip as they roll. 2 of the objects have their rotational inertias as indicated in terms of mass and radius. So we can see those values are here. The hollow sphere, 1/3 mr squared, and the disc, 1/2 mr squared. Part A, what is the rotational inertia of the hoop in terms of m and r? Give a reason for your answer. Well, the hoop is going to just simply be mr squared, 1 mr squared, not a fraction. Okay, and here's the reason. For a thin hoop, if you looked at a thin hoop, here's the center of rotation and it's rotating this way. The mass is completely and consistently distributed the same distance away from the point of rotation. And it's a large distance away from the point of rotation. Hence, it is 1 full mr squared. Another way you can kind of reason or think about it is the rotational inertia of a point mass is simply mr squared. You could consider a hoop, a thin hoop, as an infinite number of point masses all connected around the edge. Like so. That's kind of another way to reason it out. Part B, what potential energy does each object start with? Well, potential energy is mgh, so simply calculate the same mass, 0.4 times 10, times their common height of 3 meters, we get 12 joules. Part C, fill in the energy bar graphs for each of the objects. Draw a bar for the initial potential energy before the object is released, and draw bars for the final kinetic energies once it is released. So we're going to draw the initial energies and the final energies when it's at the top of the incline and when it reaches the bottom. Something to consider about this, and this is a very helpful connection when it comes to connecting rotational inertia and kinetic energy. And here's what it is. Rotational inertia relates the rotational kinetic energy as a fraction or a percentage of the translational kinetic energy. Let's see how this works. The sphere, if you remember, had a rotational inertia of 1/3 mr squared. What does that mean? It means Kr stands for the rotational kinetic energy. Kt is the translational kinetic energy. 1/3 mr squared means the rotational kinetic energy is going to be 1/3 of the translational kinetic energy. Now, the total energy was potential to start with. So our graph in each case should start with gravitational potential energy in a bar all the way up to 12 joules. Pause the video and go ahead and create the initial side of each graph. Now, since the total energy was 12 joules and the rotational energy is 1/3 of the translational, that means the two have to add up to 12 joules. And that would make the rotational 3 joules and the translational 9 joules, as 3 is 1/3 of 9. And they together have to add up to the total initial energy of 12 joules. This would produce a graph like this. You should expect 0 potential energy because you've reached the bottom, but you should expect 3 times more translational energy and 1/3 the rotational energy. So again, 1/3 mr squared relates the idea that the rotational energy is 1/3 of the translational kinetic energy. We're going to use that same idea in these other examples as well. The hoop. Well, you might remember the hoop was mr squared. Well, since the rotational inertia is not a fraction of mr squared, not 1/3, not 1/2, not 2/3, not 2/5, it's just 1 mr squared. What that means is the rotational inertias, the rotational kinetic energy is equal to the translational kinetic energy. And together, since they must add up to 12, each one of them must be 6, producing a graph that would look like this. Again, the 6 and the 6 joules must add up to the initial energy of 12 joules that we started with at the top of the incline. Now the cart is interesting because the cart it may have the same mass, but we were told that it has light wheels. Light wheels indicates no mass, which indicates the wheels have no rotational inertia. You're essentially looking at an object that does not rotate going downhill. So all 12 joules of potential energy become all 12 joules of kinetic energy. Very similar to a block sliding down a frictionless incline. For the disk, recall the disk was 1/2 mr squared. So what should that mean? If the disk is 1/2 mr squared, that should mean the rotational kinetic energy is 1/2 the translational energy. And if your energies have to add up to 12, that means the rotational energy would be 4 joules. The translational energy would be 8 joules. They add up to 12, and the rotational energy is half the translational energy. Rank the objects, sphere, hoop, cart, and disk, in order in which one reaches the bottom first. Well, completely based on the translational energy. So the cart has the greatest translational energy, that's going to get there first. The sphere has the next highest, that's going to get there second. The disk is going to get there third, that has the next highest, and the hoop is going to get there last, since that has the lowest. Again, speed is related to translational kinetic energy. Faster motion simply means you cover more distance in less time. Problem 2. Write a well-organized paragraph response to each of the following questions. A full credit response will state a clear answer to the question and connect that answer to specific physics laws and principles. Part A. The 4 objects shown below all have the same mass. Each one is pivoted about point O shown at and held at horizontally at rest. Each is released from rest and swings through the vertical position shown with the dots. 3 of the objects all have the same kinetic energy upon reaching the vertical position. The other one has the greater kinetic energy than that. Which object has the greater kinetic energy passing through the vertical position? Explain your reasoning. Well, here's our concept. The greatest kinetic energy is going to be the one that loses or decreases the most potential energy. How do you decrease the most potential energy? Fall from a greater height. Well, the uniform bar, the potential energy is measured from the center of mass. Same with the disk, same with the hoop. Therefore, the center of mass only falls that far, that height right here. The pendulum, on the other hand, the beam itself, the string itself has no mass. All the mass is concentrated at the end, which means when this falls, it has fallen a greater height. Since it has fallen a greater height, the pendulum has therefore lost more potential energy, which means that it has gained the most kinetic energy. Again, let's summarize. The pendulum has the most kinetic energy. This is because it has more potential energy to start with. It also loses more potential energy. It's another way to think about it. You can either say it has more potential energy to start with or loses more potential energy when it falls. Although each object is dropped from the same height, the potential energy decreases, the potential energy decrease of the bar, disc, and hoop are measured from the center of mass. So they are all less than the potential energy decrease of the pendulum, bob, and the string. Part B. Indiana Jones is searching an underground tomb for the Eye of Klaatu. He comes across 2 identical potential artifacts, a jewel in the center of a heavy steel framework. One is the Eye of Klaatu. It has a diamond in the center. The other is a fake and has a cubic zirconia in the center. Cubic zirconia is twice as dense as diamond. But the steel frame is so heavy that Indy can't tell by holding which one is heavier, and because he can't really lift it. He has to roll it. And he can only carry one out. He finds a fallen wooden beam that can act as a straight ramp. So he rolls both artifacts down the ramp from rest at the same time. Object A reaches the bottom first. Which one is the true Eye of Klaatu? Explain your reasoning. Well, recall that density is this variable rho, Greek letter rho, and it's equal to an object's mass divided by volume. Since both objects have the same mass distribution, or from the center of rotation, both objects have the same rotational inertia. However, heavier objects will have more potential energy. Potential energy, after all, equals mgh. More mass, more potential energy. With more potential energy means more kinetic energy at the bottom, because this translates into this when falling down a ramp. In other words, heavier objects will roll faster at the bottom of the ramp. Since object A reaches the ground first, okay, it is clearly the one that is more dense, Twice as dense means twice the mass. That means object B that loses the race is your true artifact. Part C. The B-36 Peacemaker was a strategic bomber airplane built for the U.S. Air Force from 1949 to 1959. The first prototypes had a landing gear that consisted of a single large wheel as shown in the diagram. Later models replaced the single large wheel with 4 smaller wheels. A large wheel, a cylinder, has radius r and length L, or height L. Each of the 4 smaller wheels has radius 1/2 r and height 1/2 L. The big and small wheels all have the same density. When the big wheels were replaced with smaller wheels, it was found that the bomber reached its takeoff speed in much less time. Explain why this would be the case. Include specific calculations. Well, first let's draw a comparison between the big and the small wheels. Number 1, we need to understand that the density is mass per unit volume. We need to figure out something with regards to the volume. The volume of a cylinder, by the way, is area of the base, which is a circle, pi r squared, times the height, which is L. But for the small wheel, it would be pi times r over 2 squared times L over 2, which would be pi r squared over 4 times L over 2, which would be 1/8 pi r squared L. That means since mass is equal to density times volume, and big and small have the same density, the big has 8 times more mass. Think about that. This is 1/8 the volume. This is 1, this is 1/8. That means this is 8 times the volume of this one. 8 times the volume means 8 times the mass if the density is the same. So big wheels have 8 times more volume, therefore they have 8 times more mass. Now we need to incorporate rotational inertia, because rotational inertia is what resists rotation in the first place and resists the acceleration of those wheels. Well, if we recall, it doesn't matter that what shape it is. You know, an actual disk is usually 1/2 mr squared, but I is always proportional to some mr squared. And that's what we're doing. We're going to cut out the 1/2 or any fraction for that matter and just say I is proportional to mr squared. Well, I would be 8 because the big wheel is 8 times bigger than the small one. It has a distance unit of r, radius unit of r, and so 1 squared is 1 times 8 is 8. So 8 rotational inertia units. Compare that to the small wheel, which has a mass unit 8 times less, or 1. It has a radius of 1/2, and 1/2 squared is 1/4 times 1 is 1/4. Well, 8 is 32 times greater than 1/4. So putting this all together, the big wheel has 32 times more rotational inertia than the small wheel. The big has 8 times more inertia than 4 small wheels. Think about that. If this is the rotational inertia of each wheel, times 4 would be 1, right? 8 is obviously 8 times greater than 1. Let's summarize. Since big wheels have more rotational inertia, they require more energy to rotate. With more energy going into rotation, the bigger wheels and not making the airplane get up to speed. That is why the bomber takes off in less time with smaller wheels than big wheels. Problem 3. James Bond is trying to enter a mansion by sneaking in through the backyard. There he encounters a guard that is standing in front of a clothesline that consists of a horizontal wooden plank that can pivot and freely rotate on a vertical post at point O. In order to take down the guard non-lethally and without making much noise, James Bond shoots a bullet from his silenced Walther PPK pistol at point A on the clothesline. The bullet embeds itself in the wood and the wood rotates, causing point C to strike the back of the guard's head. So in other words, bullet fires this way, causes this kind of rotation, the beam strikes the guard in the back of the head. The guard is hit just hard enough to knock him unconscious. Answer the following in brief paragraphs that cite specific physical principles. This, ladies and gentlemen, is a conservation of angular momentum problem. How do we know this? Well, one, you have some rotation and collision involved. So it's a collision between two objects and rotation at the same time. Anytime those two are together, you know angular momentum has to be conserved in this. Now, the first part of this, the second part of this is a rigid object. So the L for the clothesline would be essentially I omega. The bullet, on the other hand, is a particle. Now, here's the point of rotation. Here's the line that's moving towards, that's the line of the path moving towards the closed beam with velocity v. And this is perpendicular. There's the lever arm right there. And this would be L equals mvr. So what we have to have, in order to have angular momentum, you have to have some radius from the point of from a potential point of rotation. Part A, explain what would happen if the same bullet was fired at the same speed but at point B. In other words, right here. You guys can see that point B is clearly closer to point O, which means if the radius is smaller, the angular momentum is smaller. And if the angular momentum is smaller, the rotation of the beam is slower. The guard would be hit but would not be knocked out. The bullet has less angular momentum because there is less of a perpendicular radius. This means the angular momentum from the wood would also be less, which means the wood rotates less, smaller omega. Part B. What would happen if the same bullet was fired at the same speed at point O? Well, if it was fired at point O, you're firing it at the radius. You're firing it at the point of rotation, which means there's zero radius. Zero radius means there's zero angular momentum of the bullet, which means there's zero angular momentum of the clothesline. The clothesline would not rotate. The would not rotate at all. The bullet has no angular momentum because the bullet has no perpendicular radius if fired at point O. Part C, explain what would happen if the same bullet was fired at the same speed at point C on the post. In other words, let's pretend that you're able to fire it over here at point C at the post, not hitting the guard. The guard is kind of not at point C, but somewhere between point C and point O. In any event, what would happen? Well, clearly the beam would rotate the other way. The wood rotates the other way. The bullet has angular momentum, but in the opposite direction. Therefore, the beam would rotate in the opposite direction. And lastly, explain what would happen if a rubber bullet of the same mass were fired at the same speed at point A on the post, assuming the rubber bullet bounces off elastically off the post. Okay, this is interesting. Because now Put this all right here. Okay. So if a bullet were to strike, so it does not embed itself, instead strikes the beam and bounces backwards, that means with a change in direction, the bullet now has a greater change in momentum. Since the bullet has a greater change in momentum, the beam will have a greater change in momentum from 0, which means it will rotate much faster, hitting the guard. The bullet's change in momentum will be greater because the bullet reverses direction. Since the rubber bullet has a greater change in momentum, the wood also has a greater change in momentum. Because remember, the change in momentum of each object is the same. The bullet, the change in momentum that the bullet loses is the same change in momentum that the wood gains. And thus the final speed, the final rotational omega of the wood would be greater. It means it'll hit the guard harder. Problem 4. A rock of mass 10 kilograms makes an elliptical orbit around a dense asteroid that has big mass m, such that g times big M is 20 meter cubed per second squared. Point A is the rock's closest approach to the asteroid. Actually, from the picture, that would be a typo. It's the farthest. Let's make that correction. Point A is the rock's farthest distance from the asteroid. Part C is the closest distance to the asteroid. We can see that in the diagram right here as the asteroid is located right here. The table shows some of the values for the orbital parameters at point A, B, and C. Fill out the other values in the data table. Okay. This, ladies and gentlemen, there's a lot of things going on here, but the main concept in this would be a conservation of angular momentum problem. Okay, and how do we know this? Well, one, we've got one object rotating around another, so angular momentum is involved. But why is angular momentum conserved in this problem? Because this mass that's orbiting the asteroid is not given a net torque. There is nothing getting out there and pushing this asteroid to make it go faster or slower at various points along the orbit. Instead, it changes speed due to the fact that it is changing distance away from that mass. Therefore, L initial equals L final. Okay, conservation of angular momentum. So we're going to use that to solve this problem. L initial equals L final, which means MVR of the mass, whatever this mass is, MVR of the mass at point A over here equals MVR of the mass at point C over here. The momentum is the same. But the mass is also the same, so I could cancel the mass. And I end up, and if I solve for RA, so I can figure out what this distance is here, because I know this distance is 2 meters, I can solve for RA and figure out that distance there. So 4 meters per second is the velocity at C times 2 meters at C divided by 1 meter per second is the velocity at A, and we can see RA is 8 meters away. So this is 2 meters. Whoops. This is 2 meters right here. This right here would be 8 meters. Right here. Which means 2 plus 8 is 10 all the way across. So if the whole thing is 10 all the way across, this is cutting what looks to be the halfway point. So that would be at about 5 meters right there. Okay, so we know the distance. I'm going to color these in blue. The distance from A is 8 meters. How do I find some of the other values in here? So what is the angular momentum at, the angular momentum is mvr. So how do I find the angular momentum I can find that for A and C, because I know mv and r for that. So angular momentum of A is mvr, which would be 10 times 1 times 8, which is 80 kilograms meters squared per second. But LA equals LB, which equals LC. The angular momentum is the same everywhere, so all of them equal 80 kilograms meters squared per second. So let's go ahead and type that in, or write that in. Now I'm going to try and figure out what the speed is for the mass when it's at that point there. I know the L at mv, L is equal to mvr, but it's mvr perpendicular. See, this is the r from the asteroid, 5 meters. But we want this distance here. We want the perpendicular to that distance. So let's find that speed. R perpendicular, what would R perpendicular be? Well, if this is 8 meters, and this over here is 5 meters, well, 5 from 8 would mean that this remaining chunk is 3 meters. This is a 3, 4, 5 triangle. Makes it easy to work with here. So if I take V, the speed at B is going to be L, which is 80 over M R perpendicular, which would be 80 kilograms meters squared per second over 10 times 4. 80 over 4 would be 2 meters per second. Okay, what are the angles between R and V? Well, the angle between R and V is going to be perpendicular at A and C, so that part's easy. But what about this one here? What's that angle right there? Well, that angle is the same as this angle here. And from a 3, 4, 5 triangle, that is a 53-degree angle. Now, if you're not sure how to find that, then just go sine of theta equals, or any trig function for that matter, but it would be 4 over 5. 4 divided by 5 is 0.8. And if you take the arc sine of this, the arc sine of 0.8 is approximately 53 degrees. So you can figure it out if you don't know what that angle is supposed to be. Okay. How do we find the force, the acceleration, and the energies? Let's deal with the force and acceleration. Well, force, we're going to be using the following. We're going to be using F is equal to, we're going to use Newton's law of gravitation, big G, m of the asteroid times m of the mass over r squared. But the nice part about it is gm is already 20, so we're going to be going 20 times the mass of the object, which is 10. So the numerator is going to be 200 in every calculation. We just have to divide it by a different distance each time. So that's how easy the calculation is going to be. For FA, it's going to be 20 times 10 over 8 squared. For B, it's going to be 20 times 10 over 5 squared. And C, it's going to be 20 times 10 over 2 squared. And we get 3.125 newtons at A, 8 newtons at B, and 50 newtons at C. Now, according to Newton's second law, net force equals ma. So A would be equal to the net force divided by the mass. So in other words, 3.125 divided by the mass of 10 would be 0.3125. 0.8 and 5. So in other words, dividing each case by 10. Now, what about those energies? Well, let's take a look up here. Let's derive a few things. One, the potential energy of, this is called the universal potential energy, universal gravitational potential energy, is it looks very similar to the universal gravitation. It's big G m1 m2 over r, and it's negative, okay? And here's why. Here's the rationale behind this. If you have, let's say, a planet, and you are an infinite distance away from this planet, then essentially there's really very little to no gravity acting on that object there's really very little gravitational attraction from that planet to that object placed at point P way over here, which means essentially the potential energy is 0 at this point. So if the potential energy is 0 an infinite distance away, that means the potential energy any distance closer than 0 would be less than 0 or negative. Kind of an abstract concept, I know. But the negative applies in the equation right there. Now, if we take the idea that gravitational forces are centripetal forces, mv squared over r, we can see we're going to cancel m on both sides. We'll cancel a factor of r on both sides. And we're left with v squared equals gm over r. If we plug that into our kinetic energy formula, reminding ourselves that kinetic energy is 1/2 mv squared. So we're going to substitute v squared for gm over r. We end up with a kinetic energy equation of gm r over 2r. But I think we'll actually be good to go with this right here. Since we already have the speed and the mass, we're good to go making our kinetic energy calculations that way. So potential energy will calculate this way. Kinetic energy will calculate this way. Total energy is K plus U, so just simply add them up. Now, the total energy equation could also be written as negative Gm, big M, little m over 2R. Okay, and that's because this is our potential energy equation, which is negative, adding that to our kinetic energy equation that we derived over here. Putting 2's here to make it a common denominator of 2R means I'm subtracting 1/2 G big M little m over R minus 2/2, which is negative 1/2. All right, let's do some calculations here for kinetic energy. The potential energy, start with potential energy first. So the potential energy at A is negative G big M little m over R. So negative 20 times 10 over 8 is negative 25 joules. At B, negative 20 times 10 over 5 is negative 40 joules. And at C, negative 20 times 10 over 2 is negative 100 joules. Kinetic energy, 1/2 mv squared, so 1/2 times 10 times 1 squared is 5 joules. Adding those together, 5 plus a negative 25 is negative 20 joules of energy. Remember, guys, kinetic energy can never be negative. Potential energy can. Potential energy can decrease. Kinetic energy is not going to be negative, not going to be less than 0. B, 1/2 times 10 times 2 squared is 20 joules. 20 plus a negative 40 or 20 minus 40 is, again, negative 20 joules. And lastly, kinetic energy at C, 1/2 times 10 times 4 squared is 80 joules. And 80 minus 100 is negative 20. This should make sense because total energy remains constant. Lastly, let's go ahead and draw, as it goes from A to B to C, the energy bar graphs associated with this. Well, for A, you have a potential energy of negative 25 and a kinetic energy of 5. So it would look something like this. At B, we have a potential energy of -40 and a kinetic energy of 20. It would look something like this. And at point C, you'd have a potential energy of -100 and a kinetic energy of 80. Look something like this. Again, ladies and gentlemen, please pause and rewind as necessary, and thank you.